Hello, I am Christopher, and I'm going to be talking about our eddy current tachometer project. So for this project, we have to make a tachometer, either a fly ball or eddy current tachometer. We have to design and build our own one, and it has to be able to display the RPM of a rotating shaft within a certain range to an acceptable accuracy. The tachometer we are going with is the eddy current tachometer. It has to have some sort of actuator, like a motor, that has a controllable speed and be controlled with a mechanical device like a knob or button. This speed has to be stable for at least 10 seconds at a specified speed. For the eddy current one, we have to use the eddy current principle to measure the RPM, and we have to display this measurement with a mechanical indicator and a digital readout. And we can calibrate it using high-speed video, a stopwatch, or a given laser tachometer. And the budget has to be within $105. To start off, I'm going to explain the eddy current theory. So essentially, a fixed magnet is used to create a permanent magnetic field that is attached to the rotating shaft. This is positioned near a disc or drum that is made of a conductive material, but not a magnetic or ferritic material. As the shaft with the permanent magnet on it rotates, this change in magnetic field induces currents within the conductive material. These are called eddy currents. These eddy currents create a magnetic field of their own that interacts with the original magnetic field, creating a torque about the disc or drum that causes it to begin rotating. This cup or disc or drum is attached to some sort of spring-loaded mechanism to cause it to, instead of begin rotating faster and faster, displace a certain amount based on the torque it receives from the magnetic fields and the strength of the spring device. This spring device can be connected to an indicator and some sort of sensor to get readout, both mechanical and digital. For our design, we're using a 9-volt motor that's powered by a simple 9-volt battery. We are able to change the speed with a 10 kiloohm potentiometer to change the voltage from 9 volts to something, maximum of 9 volts to something else. The aluminum drum, in our case, is a simple and cheap aluminum can, soda can, and this is attached to a 1/4-inch shaft that is supported by sleeve bearings in order to minimize the amount of resistance it receives. The control spring in our case is a rubber band because it was something that was very weak and worked. Our magnetic field is created by a housing that holds 2 cylindrical neodymium magnets with their poles facing opposite directions. And the whole thing is, the whole housing is 3D printed. All the blue pieces you see in the image here are 3D printed, making it cheap and simple. This whole thing is controlled by an Arduino R3 with a 1602 LCD display to display the digital readout. Our bill of materials, as you can see, is very cheap. Almost all of the cost is in the Arduino kit that included the display and the potentiometer and many other things that we didn't use. So if this were to be scaled up, we could find a more specific set of things that would make it even cheaper rather than buying a kit that includes a bunch of things that we did not use. And now Daniel and Bryan are going to talk about the physical product that was made.
So as you can see in the image here, our circuit connecting the motor to the electrical side is actually very simple. On the right hand side of the image, we have our 9-volt battery, which is connected to a breadboard via simple jumper cables. And in the middle of the breadboard, you'll see that the power is being routed directly to a potentiometer in the middle there. And based on the positioning of the knob on top of the potentiometer, the voltage that the motor sees will either be fully closed at a 0, so the motor will not be actuating at all, or it will be fully open and our motor will be operating at full capacity. Looking next at our rotary encoder, this is how we chose to decide our digital display output. So the interface from the rotary encoder connects directly to a shaft, which is on the output of our eddy current tachometer. And based on the number of turns, those signals are then interpreted by our Arduino, and this is sent to our digital LCD display.
Now we'll go into the evaluation, including calibration of our system. Using the phototachometer as shown on the right, measurements were taken and dialed from a mechanical point. The highest RPM we achieved consistently was 5,400 RPM, and the lowest 3,600 RPM. Another consistent RPM of 4,500 was also measured and recorded. Measurements in RPM fluctuated about 100 revolutions per minute, and the most consistent reading was recorded. Now we will go into the demonstration of our system. The first video to be shown will be demonstrations at 54 and 3600 RPM. The next will be tachometer readings. Concluding our project, we now see that our eddy current tachometer was created under budget of 57 and 39 cents. It featured neodymium magnets, an aluminum can, an aluminum foil casing, rubber band tensioners, and 3D printed frame and assemblies. Our tachometer was able to read a consistent RPM of 5,400 to 3,600 RPMs, and it featured a compact and quiet build with the only sound mainly coming from the motor. Our biggest challenge was definitely achieving consistency, whether it being the clearance of the magnets and the aluminum can, or also choosing a correct tensioner, or in this case, a rubber band tensioner, because metal tensioners were too strong, or also our motor, which blew out our very first time. They were all very simple mistakes that were able to be overcome, but it just goes to show the level of sensitivity that these components can incorporate into our system. And finally, here are a list of our references. Thank you.